Hello again. This is the second flipped class meeting or recording to cover a new class demo that I will use to better explain some of the concepts we are going to cover in class. Yet, some of the concepts maybe are not covered yet in class. I'll give a brief introduction about them to be able to use them in the demo. So you'll find them handy when we talk about them in class, and I won't have to do what I'm going to do in this recording in class to save more time and cover more advanced topics. After we finish the video, what we're going to develop together, the code we're going to write is going to be available on eLearning under the class demos section. In this meeting, I'm going to write with you some code to we're going to write code to convert a hex 16-bit number to first BCD, binary coded decimal, and ASCII, the ASCII code for each decimal number that we get in the BCD. This would enable us to use some new instructions that I want to cover. We're going to learn about division, how to divide numbers. We're going to learn about branching instructions. And we're going to learn about, I prepared three things. Execution time. Execution, how we to compute execution time of instructions, and we're going to do delay loops. So this is the goal. To start, we will have a number, a 16-bit number in memory. Let's say at the very first memory location, 1000 of the SRAM that would reserve two locations. Let's call this num1. And this number, let's assume it is, for example, let's assume 1, 2, F3. Let's see what is this equivalent to. 1 to F3. If I go to my calculator, hexadecimal 1 to F3 is equivalent to 4851. 4851 decimal, 4851. This is equivalent to 4851 decimal. Our purpose is to generate the BCD. So num, and let's call it num1, num BCD. Let's call it like that. The num BCD, I want to separate the 1 alone, then the 5, then the 8, then the 4. I want to take each of these decimal numbers by its own. This is requirement number 1. Requirement number 2 is to get the ASCII code the ASCII code of each of these numbers. Okay, so to get an ASCII code of a number, you add 30 hexadecimal for it. Okay, so the 4 will become 4 decimal, or it will become hexadecimal 34. So if you send it, the purpose here, if you send it over a serial link that, or any display that displays ASCII characters, you will see a 4. Okay, and same for everything. So we want to add 30 for each, 30 hexadecimal or 48 in decimal to each of these numbers. Okay, in hexadecimal, to get the ASCII code for each number for displaying purposes. Now, we're going to start with a small example with 4 digits, but I don't want to do it 4 times. I'm going to use loops here. I'm going to do something and repeat it 4 times to learn about a new concept, the loops, that where we will utilize the branching instructions to do loops. Okay. And to split these numbers, how would we split? We have a number 4851. 4851. How do I get a 1? You can just divide it by 10, right? Divide it by 10. You'll get the result will be the quotient, we call it, will be 485, and the remainder will be the 1, right? Then, so we got the first digit, digit 1. Then we take the quotient again, the 485, divide it by 10, you will get a 48, right, for the result. This is the quotient. And the remainder will be the 5. Okay, the 5. And this is digit 2. Then you take the 48, divide it by 10, you get a Q of 4 and the remainder of 8. And this is digit 3. And what I'm doing here, this is digit 1, digit 2, digit 3, digit 4. Okay. Digit 3 is the 8. Then 4 divided by 10 equals 0 for the quotient, right? And the remainder will be 4. And this is digit 4. I'm not going to do these steps 4 times. I'm going to do it once. Okay, do it once. And repeat 4 times. So in case we have longer numbers, 10 digits or whatever, you could just repeat more. Okay, so this is the purpose. This is what we want to do. So if we have our number, the 4851 here, in hexadecimal, it will look like 1, 2, F3, sorry, F3. Okay, this is our num1. Then I need 4 locations for the BCD. Okay, then here 4 locations for the num BCD, and here let's call it an ASCII, and BCD, and BCD, and an ASCII. So an BCD, 4 locations, then 4 locations, 1, 2, 3, 4 for the an ASCII. Okay. Tamam. So here, the result, I'm going to write it in blue. This is what should be computed. I should get, depending on how we want to store them, maybe if we have, keep the, so the 4 maybe here, the 8 here, the 5 here, and the 1 here, then their ASCII will be 34 hex. Then the ASCII of the 8 will be 38 hex. then the ASCII of the 5 will be 35 hex, and the ASCII of the 1 will be 31 hex. So these are to be computed. By the program. Okay, let's go write the code. Start code warrior. File, new project. Same microcontroller as last time. Assembly. Set the folder we're gonna store in, and let's call it, create a folder, call it class demo 3. Okay, save it here in this folder. Next, finish. And here we get our code. So as last time, let me take these, okay, these numbers. So we're going to use pointers, okay? So first I'm going to take this, and then I'm going to make a pointer, for example, here, X, point here, then I start storing at X, comma 3, right, here, then I decrement X, so it will point here, then here, then here, repeat a loop 4 times, okay, then take every one of them, add 30, save it in a location, then change the value of the pointer to the other location, the other location, the other location. Tamam? Okay, before doing that, actually before writing code, I want to revise with you real quick some of the instructions we're gonna use. The division instructions. We're gonna use one division instruction. Here's a summary. Last time I showed you this table, you saw it, the multiplication and division, okay? Multiplication and division, we looked at the multiplication. Now for the division, we have the eDiv. This divides unsigned 32 number by a 16-bit number. The numbers, there's no operands you indicate when you write your code. The operands are fixed. They have to be, the numbers you want to divide, the 32-bit have to be N, Y, and D in this order. Higher 16-bit in Y, lower 16-bit in D. You divide them by X, okay, the 16-bit number. After you say eDiv, you find the quotient, the result in Y, and the remainder in D. Okay, 32 by 16. eDiv S, this is for signed 32 by 16 division. FDiv is for fractional dividing fractions. iDiv unsigned 16 by 16. iDiv S is for signed 16 by 16. So in our case, we have a 16-bit number, right? In our case, we have a 16-bit number. We want to divide it by 10, right? 16-bit by 10. So I guess we can use the iDiv, this one, okay, iDiv. So let's write it down, iDiv, D divided by X, the result is in X and remainder in D. So iDiv, so we're going to use iDiv, right? 16 unsigned, 16 by 16. Division, the number should be in D divided by X, no, Y, sorry, D by X, and the result in X, remainder in D. You divide D by X, the result is in X, right? And the remainder is in D. So this is the instruction we're going to use when we want to divide by 10. Okay. In the class, we're gonna look deeper more into these instructions maybe. The other set of instructions I want to show you are the branching instructions. The branching, you can branch. What does branch mean? We know that the program counter points to a memory location in program memory where an instruction will be fetched, right? Then after fetching this instruction, while it's executed, the program counter increments to point to the next instruction. So instruction 1 is here, right? Then instruction 2 is here, and so on. It keeps moving sequentially. Nothing can change this sequence unless there is a branch instruction that tells the program counter to go to a label, مثلا, to address 1000, so it will or 4000. So if the program counter was here and found a branch to 4000, it will go back to 4000. Okay, this is how we can control the flow of the program counter. Okay, now there are conditional branch instructions and unconditional branching instructions, which means branching can be unconditional. You always branch, just like this branch. We used it in our previous class demos when we did infinite loops, right? Or never branch to a location. You provide this location, relative 8-bit, or if you want it long branch, L for long, you can provide something, an operand here, 16-bit, which can send you further, okay, back or forth. Okay, the conditional simple branching instructions, conditional, they are based on conditions, the flag conditions, the carry flag, zero flag, negative flag, etc. So here you say, for example, a branch, if the carry flag is cleared, if the carry flag is cleared, yani 0, you branch to this location. If not, you continue the program counter. You here branch if the carry flag is set, S for set. Yani if the carry is 1, you go check it in the CCR register. If it's 1, you branch, yani true, else you don't branch, you continue. Branch if equate, yani the 0 flag is 1, yani the number is equal to 0. Okay, branch if minus, branch if not equal, yani 0 flag is 0. The result of the previous operation is not 0. Okay, and so on. So you check all the flags. Unsigned branches, when you compare numbers. So you do a subtract, for example, or a compare instruction. Then you say branch if higher, or branch if higher or same, branch if lower, branch if lower or same. Here are the same, but for signed numbers. So you don't say branch if higher, you say branch if greater, if greater. Okay, so a number, two numbers, 0, 0, 0, 1. Okay, and a number f, 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 1. What is higher? F is higher than this one in terms of counting. But is it greater? If we're talking about signed numbers, this is a 1, this is a negative number, right? So this would be greater. Okay, these are some branch instructions, more branching instructions. Before you branch, you need to set the flags, either subtract or compare. I'm going to cover these things. Subtract, but without storing the result. There are also more branching instructions, like here where you decrement and branch of equal. You have a counter, you decrement the counter. The counter here has to be a register. Okay, you decrement, you want to count 10 times, you put in A 10, you decrement and branch of equal A. If it's equal to 0, start 0, you always decrement. If it reaches, when it's reached 0, you do the branch, otherwise you don't. So okay, so you check a condition or not. So you can do a loop for 10 times, if you put in A10. Decrement and branch, if not equal, you branch. So this is if equal, you branch. This is if not equal, you branch. These are for increment, and if you reach a 0 and you overflow, the counter reaches 0, you branch. It does not, you branch, and so on. Okay, here this is a test. You don't increment or decrement. You just test the value of the counter if it is 0 or not. Tamam. These are some instructions I wanted to show first. Okay. طيب, let's go and start writing our code to do this, what we planned for here. I'm going to take it on my other screen to say track. Okay. We started the program. We started, okay, I have a new project. Let me just clean up here. I don't need these data memory variables. I don't need this program already written here. Okay. So here in the RAM start, where I want to define my data, okay, let me define my num1. We said num1 define constant word. It is a word, right? Right, and we choose to have it as hexadecimal. What was it? 12F3, 12F3. Okay, and this is equivalent to decimal 4851. 4851. Of course, this is to verify later that we're going to compute it, make our program compute it. Then we're going to book 4 bytes for the number, the BCD numbers, because they're 4 digits. Each one of these should be stored in one location. Okay, so we need 4 locations. We book them. So we can say number ask BCD and BCD reserve memory bytes 4 locations to store the 4 digits BCD digits later. And then we have an ASCII. We also need for each of one of them, we need a location. We reserve 4 more location. Okay, and here this is to store the 4 ASCII codes later for the 4 digits. And in my code, I'm going to do something. I'm going to divide by 10, right? And store somewhere. So I'm going to do this 4 times. So I want to, instead of repeating it in the code 4 times, I'm going to do a loop 4 times. So I need for the loop a counter, okay? Yeah, a counter that counts to 4. So a byte would do it. So let's say define something called counter 1 مثلا. Define constant byte and put 4 in it. Loop counter. Okay. What else? Anything else here? I don't think so. We can go directly and start writing our code here in the main loop. We can write our code. So the first thing we want to do is to make something to bring the BCD number and divide it, right? And when we said we want to divide the instructions to divide, the divide instructions here, the IDEV, we need to put the number we want to divide, which is the num1 in D and the 10 in X. Okay, so this is the first step. So we're gonna and after we finish this, we want something to point to where we want. So X, we cannot use it because it's we cannot use X as a pointer right now because it's part of the division process. So we'll use Y. Okay, so I'll use Y to point to where we're going to store the BCD result, the computed BCD result. Okay. طيب, so we load Y with the address of where we want to store the NBCD. Okay, the NBCD. So here Y points to where we want to store the resulting BCD. Okay, in this case, BCD Y will get the address of the address of the memory location BCD. So it's going to be BCD here. We booked 2 locations, so address 1000, 1001. So it's going to be 1002. Okay, so 1002. Y is going to be 1002. Then we load the number we want to divide into D. Okay, what do we want to divide? Num1. Num1. We load it. Okay. We go to memory and get it. I don't put a hash here. Okay, you don't put a hash here. Otherwise, you'll get D will be 1000. You put num1 directly. Can add from address 1000. Okay, so D after this instruction will have the first number, which is which was the 4851, the 4851 decimal. Okay, then we load the number we want to divide by the denominator with a 10. It should be in X. We load X with directly number 10. We want to divide by 10. Okay. Numerator is ND. Denominator is NX. Okay. Then we say, and before we divide, because the division needs to be repeated 4 times, we need to have a counter. Well, the counter is already loaded, so no problem. We can just use it. Right? The counter is already loaded with 4. We don't need to. It's initialized. So actually, we can start the division. So idiv. After executing this instruction, as per our notes, the quotient, the result will be stored in X, and the remainder will be stored in D. Okay, and this is what we want to store. This is our first BCD. Where do we want to store it? Where do we want to store it? Here, right? So we want to store it here. We just got the 1. The first division, we got the 1, so we want to store it here in the bottom. So if we make X point here, so this will be 3 comma X. Okay, 3 comma X in the direct addressing mode. So we we choose to use Y. So we can say store accumulator, and we know the result is in D, but it's not. Our result is a number between 0 and 9, so it's not more than 8 bits, right? So we don't need D all of D. So we load the lower part of D, which is accumulator B. Store accumulator B at memory location 3 comma Y. Okay, 3 comma Y. We stored our first accumulator. Then I don't need the remainder anymore. I need to get the quotient and divide it again by 10, right? So we exchange X and D. Okay, now X is in D. So what now D will be 485. We release the 1. Now 485 is in D. Okay, now I can go back and repeat the division and store and exchange and store and exchange 4 times. But we need to adjust our pointer here, the Y pointer. That is, we said this is not, we're not using X anymore, we're using Y, okay? Instead of making Y plus, Y plus 3 here, if we can decrement Y upwards, so our effective address will become here, right? So we store the 5 here, then we decrement, we store here, then we decrement, we store here. We keep decrementing 4 times, which is the value of our counter, okay? So this is what we're going to do. So we're going to decrement Y before we branch, decrement Y. This is an instruction called decrement Y register. Then we decrement the counter 1, decrement counter 1, okay? And if it is not equal to 0 yet, yani we still need to do more times, branch if not equal to 0 to again. And again is load, then divide, right? Load, no, we don't need to load. We already loaded. X, we need to load X with 10 again. So but the D, we already exchanged, right? Here, we already exchanged. So D has its value. X need to be reloaded again. So again will be here, okay? So this is the loop that repeats 4 times here. Somebody can ask a question, why didn't we use one instruction to replace these two with a decrement and branch if not equal, DB and E? That is valid if our counter is not a memory location, if it was a register, okay? But since it's a memory location, there is nothing we need to split, okay? The DB and E only uses the counter, has to be in a register. After doing this 4 times, our the BCD numbers will be stored in their 4 locations. Now, next step is to add 30 to each of them and make, now we have these 4, 8, 5, 1, we have them here. Now make another pointer, Y point to here, plus 3 طبعا, and add 30 to each of them and store in the same order, okay? 4 times. Okay, we need to reinitialize our counter and everything. Okay, so let's make let's load make a pointer point to the BCDs. No division here again, so we can use X, load X with the address of memory location pointing to NBCD, right? NBCD. Now NBCD here, X will have memory location. NBCD here is address 0122, right? 1002. And make another pointer, point to where we want to store the result as the ASCII. Use Y, load Y with the address of where the ASCII is to be saved. So the ASCII Y here will point to address what will be ASCII. So these are 0, 1000, 1001, and here 4 bytes, 2, 3, 4, 5, 1005, then here 1006, 1006. Okay, the ASCII, the first location of where we're going to store the ASCII. We loaded them. What we want to do is get a byte by byte from where X is pointing at, add 30 hexadecimal to it, and store it where in the location where Y is pointing at. Increment the counters, right? And decrement, increment the pointers to point to the other location. Decrement the counter. If it's not 0 yet, repeat again 4 times until the counter is. We need now I'm going to try to use the counter, use the other instruction, the decrement and branch if not equal, where our counter has to be a register. D is free. Register B, for example, we want a counter of B of 4, sorry. So we can say load accumulator B with an immediate number of 4, counter of 4. Okay. Then we can start load accumulator A with 1 comma where X is pointing. X is pointing to where we just did X is pointing to the BCD here. Okay, the first location plus. So we do a post increment. So when after we load, we make it point to the next byte, Okay, then we add to A an immediate number hexadecimal 30. Okay. يعني load BCD digit convert BCD digit to Ascii code, okay, by adding 30 hex. طيب, then we store. Now the result is in A, we store it. We're done with it. We can just go store it where Y is pointing to the BCD, right? We just made Y point to the Ascii, sorry, and Ascii here. Okay, so we can make Y store accumulator A 1 comma Y plus post increment. So store it, then make Y point to the next memory location for the next common store. Store Ascii code in memory. Okay, and the counters now are pointing to the next byte, second byte. Okay, I can repeat this 4 times, or I can put it in a loop. Okay, my loop counter is in accumulator B, counter of B of 4 in register B. Now we can decrement here, decrement and branch. If not equal to 0 yet, yani I still have to branch register B to again, but I cannot use again because it will confuse it. Let's say again 2, and again 2 will be at when you load the second BCD digit, so it will be here. Okay, again. After this loop is done, and 4 times, when B becomes, so first time is 4 minus decrement 3, 2, 1. The last decrement is going to be 0, so it's not going to branch. So you did it only 4 times. Okay, so when it doesn't branch, it continues. Here, we're gonna be done. What do we want to do? We can do turn on the 7-segment displays on port H. Or how about we make port H blink? We already have the concepts. I just want to introduce something. So we're done. We converted. We can debug and see everything. Let's try to blink any. Let me write the code here, write some comments here. This part here, we start here. Here, convert to BCD. Then second part starts here. Convert to Ascii. Then third part here, maybe blink 7 segment display. How do we blink this? Turn it on, turn it off, turn it on, turn it off. We used to turn it on only, but how do we turn it on and off? We cannot say turn it on, turn it off immediately without any delay in between, because you will not see it turned on for a few microseconds and then turn it off. So we need to do some delay. So here we're going to learn how to do delays. I'm going to cover the details in class, but this is to save some time when we do the demo. Okay, to save some time, so what the skeleton will be, first we want to make port H as an output, so we move a byte immediately, FF hex, yani ones in all bits to register DD. We already did this in the past, DDRB, DDRH, sorry, DDRH, and here we made port H. Port H is output to be able to turn on the LEDs. Then we want to turn on the LEDs. I'm going to write a comment. Okay, how do we turn on the LEDs? We write zeros to port H because we said it's a common anode, so a zero will turn on an LED. So we can move byte again immediately, hexadecimal FF for the whole, all LEDs on port H to PTH, turn on all 7-segment display, 7-segment display. Okay, then here we want to introduce some delay. Let's say 500 milliseconds delay مثلا, نص ثانية, half a second. Then we turn off the LEDs. So we move zeros to port H. Oh, sorry, to turn on we move zeros. To turn off, we move ones, right? So move byte immediately, FF to port H. Here what we did is we turn off 7-segment display. Okay, then we delay for 500 milliseconds. Then, so you turn on, you keep it on for half a second, you turn it off, keep it off for half a second, and keep doing this forever. Here we can do an infinite loop, branch to forever, and the forever here will be where we turn on here, forever. So it will, after computing what we want, we can keep blinking the 7-segment forever. Okay, now the challenge here is to do the delay, the 500 millisecond delay. So let me introduce this concept. We're gonna talk about it more in class. Timing in the SCS12 relies on something called the E-clock. The E-clock is half of the crystal oscillator. Okay, so if my oscillator frequency is 8 megahertz, for example, the E-clock will be 8 megahertz by 2, which equals 4 megahertz. Okay, if it was 16, this will be 16 by 2. That's it. Now, how do we know how many instructions how many E-clocks each instruction consumes? You can go directly to the data sheet, the CPU manual, for example, and check, for example, let me open it real quick. Okay, here I can Control F, search for, for example, instruction push accumulator A. Push accumulator A. You go count these letters 1, 2. So this takes 2 E cycles. طيب pull A has 3 letters here. Okay, 1, 2, 3. So it takes 3 E cycles. Now, what does the letter mean? There is an explanation upwards that this F, for example, free cycle. CPU is busy, but the memory bus, the memory access is free, and you can use memory, etc. Okay. Nope instruction. Where is the nope instruction? Here, the nope, only 1 E cycle. Okay. The decrement and branch, if not equal, for example, takes 3 cycles. Okay, and so on. So you can figure out how many cycles each instruction consumes. So if we can do something like this, if we can do a loop like this one, I'm going to copy it actually. The push A, we just checked, it takes 2 E cycles. The pull A takes 3 E cycles. So these two together take 5, plus 5, 10, plus 5, 15, 20, 25, 30, 35, 36, 37, and the decrement branch not equal is 3, so 40. So this piece of code consumes 40 E clock cycles to execute. طيب, in our case, how many E cycles do we need? First, we need to check our clock oscillator. What is the frequency of the clock oscillator? If I remember well, I'm not sure. Some of the boards had 8 megahertz or 16. I think this one is 16 megahertz. We can check it. Let's work on 16 megahertz. Okay. So if we do, let's do the math. Oh, sorry. Let me bring this board back here. Okay. So let's do the math. If my oscillator frequency equals 16 megahertz, okay, my E clock equals 8 megahertz. Okay. Then the time of the E clock. Okay, so the E clock will be like this, right? Repeating itself, 8 megahertz. The time it takes for a cycle, one full cycle T, is this, 1/8 megahertz. Okay? So this is the time. And so the push A instruction will take the push was, how much was the push? 3 or 2? The push was 2, I think. The push was 2 E cycles. Push will take 2 E cycles, which is equivalent to 2 times 1/8 megahertz, which is equal 1/4, yani 0.25 microseconds. So this will take 0.25 microseconds. طيب, how much time will this subroutine take? These 40 E cycles take. 40 E cycles, 40 E cycles will consume 40 times 1/8 megahertz T. Okay. Time, which is 40/8 megahertz. 40. Where is my calculator? Here it is. Okay, let me go back to scientific. So 1/8 megahertz, 1 divided by 8 million. This is the 1 E cycle, times 40 equals 1, 2, 3, 4, 5, 6. So 5 microseconds, right? 1, 2, 3, 4, 5, 6. 5 microseconds equals 5 microseconds. Okay, if we want to do a delay of 500 milliseconds, this is a micro, 500 milliseconds, then this has to be repeated how many times? Repeat how many times? Divide 500 milliseconds by 5 microseconds, right? And this will be how many thousand? Clear. So 500 millisecond, which is 500,000 microsecond, divided by 5 microsecond, which is 100,000 times. 100,000 times. 100,000 times. 100,000 times. 100,000 times. Okay. So if we put this code inside a loop like this and repeat it 100,000 times, we get what we want. Okay. However, there's no register that can take the number 100,000. Our registers, the biggest one is X, for example, 16-bit. It can take a number of 65,536, right? 16-bit. So maybe you need to do 2 loops together, like something like this. So do 50,000, then repeat it twice, for example. About our clock oscillator, I think it was 8 megahertz. Wallahi, I'm a little confused. If our clock oscillator wasn't 16, if it was 8 meg, then this would be 4 meg. Okay, and then here you'll need not 100,000, 50,000. Okay, 50,000. In this case, one register will take it. I did it. I used it before, and this number clicks in my head. So I think it is probably 8 megahertz. So this will be 40 times 1/4 megahertz. Okay, and this will be 40 over 1/4 megahertz for yeah, and this will be 10 microseconds. Then you repeat 50,000 times. Let's work with this. Let me go copy this code and repeat it. Where's the code? The loop time here, the 40 E cycles. I'm just gonna go copy this loop. Okay, copy and put it here. Oh yeah, and we're gonna deal with something called subroutines. I'll cover it in class. See? Okay, so this will, if, and let's write, say, here a comment, if oscillator frequency equals 8 megahertz, then E clock is 4 megahertz, right? Which is equivalent to time 1/4, which is 0.425, 25 microseconds. Okay. Okay. Times 40 times 40 times, okay, times 40. This will be 10 microseconds. 10 microseconds. So each loop will take 10 microseconds. We said we need to repeat this 50,000 times. So we can do something here. So this loop, let me take it out. Let's initialize a counter here. Load X here, X. Load, we can load X up to, load X. We can load it up to immediately with number 50,000. And this is not hexadecimal because we can load it up to F, which is 65,000, 503.60. Okay, but anything above, you cannot put it in one register. If it's 100,000, you need to do two loops. A loop calls a loop. 50,000, and the loop will be here. Okay. So times 50,000 times, you'll get 500 milliseconds. Okay, there is something. Now I want this delay. I can do two things. I can either copy this code, put it here, and put it here again, but we can say something like, and the loop, no, the loop doesn't point to load X. We cannot load X with 50,000 every time, right? So this will be an infinite loop. So the loop will be here. The loop will be here. Okay, the loop will be here. Let's put a label here, call it my delay, my 500 millisecond delay. Okay. My 500 millisecond delay. We can call this as a subroutine, as you call a function. We explain it more in class. So here we say branch to subroutine, which means the current location will be saved in the stack, so you can return back where you were here before the branch. Branch to subroutine, my 500 millisecond delay. Please, if you have any issues here, ask me about it in class when we explain the subroutines. Okay, this will send the program counter here. It will branch. Then we should have a return from subroutine at the end. When this is over, you return from subroutine to the place where you were at before the branch. So when we executed the branch, the program counter was here at this move. Okay, so we'll go back here. Now we want to repeat this again. So we can copy this, do it again, and call the delay again here. Okay. So you turned on port H, delayed 500 milliseconds, turned it off, delayed 500 milliseconds, then keep doing this forever. Okay. Let's build our program, run it on simulation to check the numbers if they match what we did using the calculator. Let's run. Where did we store the result? We stored the result at memory location, the BCD and the Ascii. The BCD is at 1002 and Ascii is at 1006. So let's go here at memory location 1002. You'll find this is the original number, the 12F3, that is equivalent to the 4851. So here are the 4851. Then following 30 hex added to each of the 34, 38, 35, 31. Okay. Tamam. So this is the computation. The math is correct. For the blinking, let's try it Let's try to then run the program on the microcontroller. So let me connect my microcontroller here and see if the blink works. Let me program it. Load, set the switches, load, reset. Then here, pick serial monitor, program, COM3, I think it was. Why does this happen again? It was COM3, it doesn't change. Okay, let me close this. طيب. Reset, close this again. Okay, close, program. It is flashing, erasing flash memory, putting the new program in place. Now I can switch back to run mode here, run. And the 7-segment display is not blinking because maybe the clock was slower. طيب, let me try this thing. Excuse me. It may take long. I want to reprogram this again and try this thing. I'll tell you about it. What I did. I try. Okay. Now, this is annoying. Okay. Close this. Turn on. Okay, programmed. Run from by clicking the green arrow. Okay. This is on. Is it slow or what? Is it slow or what? It is running. Okay, cancel. Wallahi, what's wrong? It looks like we need to debug. Branch forever. My 500 millisecond delay. Load X 50,000. Did we do the math right? Decrement in branch if not equal X to loop. X to loop. What is making it not work? So too slow. Too slow. Let me just divide this by 10, the loop, just to make sure. Okay. Program again. I have to take it out every time. Cancel, okay. Run. It turned on. It didn't turn off. Are we turning it off? We stored the 0, turning it on, delayed, off, delayed, and we branched again. The logic seems to look right. Okay. Why is it not turning it off? Run. Weird. Okay. Load X. Push. Decrement. And branch if not equal to 0. The thing is, Okay. Well, I want to single step. Okay, let's do this by let's check the simulation first. Let me see a single step. Let me single step. Let me single step. Let me go back to simulation. Make this back 500, 50, 5,000, 50,000. Run it in full chip simulation. What I want to do, look at these things I'm going to try to do. I can go here to the code and say run to this point. Here I can say run to cursor. Now we're here. Our results are there. Port H. Port H is something address. Where's port H? PTH. It should be address. I think port A is address 0. Address 2 is no, I didn't choose address. Address 2. Oh yeah, 2. I think. Oh yeah, 8. I think it's 8. طيب. Single step. Delay 500 millisecond. I want to skip this. Or you know what? I want to go there. Now, what's going to happen? I'm going to go through the loop, keep doing this for 50,000 times. And I'm not going to press this button 50, turn from subroutine. So I want to run to cursor. Run to cursor. Can I go back? Okay, to here, run to cursor. Looks like we're stuck in this loop. What's wrong? What's wrong? RTS loop. Okay. Let me try different register. I have something I wrote in the past here. Loop. Copy. I want to try this. Well, the same thing, the same code. Control V. Same thing. Okay. Here, just call it delay. 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 Okay. Branch to subroutine. Yeah. Okay, run. Let me try this. Here, go to address 8. Okay. Here, go to run to this cursor here to turn off. Delay. D is not equal. What is D? It's not FF yet. D should decrement every time, right? See, every loop, it should decrement. Okay, what happens when D is 0? How is there a way to make this 0? Okay, no, it didn't work. Okay. Can I run to this cursor? Can I? Yeah, it worked. Now I think it worked. Let me just try to put it back. I don't know, something could be the register or so. The only difference is we changed the register X with D. Let me try this. Full chip simulation, use serial monitor, program, and run. It is blinking. See it blinking. So the code, the logic was correct. I don't know what was the problem. Register X or register Y. Maybe we need to look more into it. But we're done. The LEDs are blinking, so our loop is working. Thank you very much for your time, and see you in class. See you in class.